All right, moving on. Let's continue our topic of logarithms. So we'll do some evaluations. It says evaluate the following expressions with logarithms. So in our first example, we have log base 2 of 32. We want to find its value. All right, so keep in mind now our definition, which I'm going to go ahead and put back up here. What defines a logarithm? Remember, a logarithm is defined, all right, as an exponent. So we just got done converting back and forth between exponentials and logarithms. So yeah, log base a of x equals some number y if and only if a to the y power equal x. All right, so with that said, log base 2 of 32 equals what? We want to find its value. We want to find its output, right? We want to find that number y, right? So that implies what? 2 to what power is 32? Right? So what power do you raise your base to get what you're taking log of? That's how you evaluate logarithms, which you should know that's what? 2 to the 5th power, right? It's 32. Now, if you wanted to, you could even prove this with exponential properties. So just to show you, again, in finding y, you want to give it a variable 32, you could even rewrite it base 2 if you didn't see it. 2 to y. 32 is the same thing as 2 to the 5th power. And we know from properties of exponents, right, if the bases are equal, right, in this exponential equation, then these exponents are equal. So that implies y equal 5. So yeah, log base 2 of 32 is equal to 5 because 2 to the 5th power is 32. All right, how about our next one? What's log base 3 of 1/27 equal? Let's find that output. Let's find that number y. So log base a of x equal y, then a to y equal x. So 3 to what power y equals 1/27. And I'm going to do this one the same way. I'm going to rewrite this with the same base. So I'm going to solve this exponential statement using properties of exponents. We know that 1/27 is 1/3 cubed, right? So I like that. I'm able to write both of these base 3. And with that said, I'm going to go ahead and get rid of this fraction and bring 3 cubed up to the numerator. And we do that, we change the sign, right, of the exponent. So it'll be the same thing as 3 to the negative 3 power, which implies what? Y equal negative 3. So yeah, there's our value. So find our value using a exponential. All right, how about example C? Log base 2 of 2 to the 8th power. Well, this is one of our properties. We talked about some simplifying properties. I talked about our same base rule, right, which this is actually a composition property. You plug an exponential into a logarithm. Well, if they happen to have the same bases, a and a, log base a of a to the x power always simplifies to x, right? Same thing goes for powers, right? A to the log base a. So if you put a logarithm into an exponential with the same base, it simplifies to x. So composition, right, of inverses. So remember, exponentials and logs are inverse to each other, so their composition is always equal to x. Simplifies to your exponent. So log base 2 of 2 to the 8th power is equal to 8, right? That's our same base rule. All right, same thing goes for natural log of e to the negative 1. Let's go to example D. This is log base e, right? Natural log. Well, again, you got the same base, so it simplifies down to x, which is your exponent. All right, same thing goes for example E. We got our common logarithm. That's log base 10, if you want to write it with a base, of 10 squared. So again, same base rule, right? So that equals 2. All right, and I mentioned earlier, you can put a log into an exponential. So look at example F. Got e to the natural log of 3. Again, natural log is a logarithm base e, so we have that same base property. Well, it equals what you're taking log of, equals x, equals 3. So again, there's that same base rule, a to the log base a of x equals x. All right? And then 2 to the log base 2 of 9, well, that's going to equal 9, right? Same basis. Simplifies what we're taking the log of. Now, let's look at some other properties of logarithms. As we talked about our properties, we talked about our power rule, our quotient rule, and our product rule. And our product and quotient rule and power rule allow us to simplify our expressions. So if you look in this example, it wants us to find the value of these logarithms. Well, let's look at 2 times log base 3 of 4. Let's see if we can go ahead and evaluate this one. Well, what I want to do is use my power rule. So I know that the power rule, I'll write it over here on the side. All right, our power rule allows us to take a coefficient like 2 and bring it back up into the exponent. Because it states log base a of m to some power p equals p times log base a of m. So yeah, we're going from here to there in this example. So yeah, we can bring that power up here. So this will be equal to log base 3 of 4 to the second power. So using the power rule right here. So we'll make that note. I'm applying the power rule in this example. Now with that said, we've got minus log base 3 of 48. So again, I'm simplifying this expression. Log base 3 of 4 squared, that's log base 3 of 16. So we'll go ahead and square it. And now, in my last step, I'm going to go ahead and use the quotient rule. So I've got a difference of logarithms. So we learned in the quotient rule, I'm going to write it up here above it. All right, the quotient rule allows you to take a difference of logarithms and combine them into one. It states that log base a of m divided by n, for example, equals log base a of m minus log base a of n. So quotient rule forms a difference, product rule forms a sum. So when I see that minus sign, right, I can go ahead and use the quotient rule here. So I'm going to put QR here. So that's equal to log base 3 of 16 divided by 48, right? There's the log of m, right, over n. So using the quotient rule here. So again, I'm taking this, right, and dividing it into 1 by dividing. So again, I'll draw that little arrow here so you can see where that came from. Now, what is 16 divided by 48? Let's go ahead and reduce that. We know that 16 goes in 48 3 times, so we can reduce that to log base 3 of what? 1 over 3, 1/3. And then we're back to our definition of a logarithm, right? What are we doing with our log, right? What power do you raise? So we want to know what it equals. Again, if you want to write it out as exponential, you can. We want to find that number y, right, that satisfies its logarithm. So that implies 3 to what power y, right, would equal 1/3. Well, we should know that's -1, but you could even prove it using exponent properties. We can bring that up, right, by changing the sign of the exponent. That's 3 to the y power equal 3 to the -1 power. So bases are equal. We know the exponents are equal. So y equal -1. So yeah, what does it equal? It equals -1. So we've evaluated that log using the power rule, right, and the quotient rule. So the power rule allowed me to get rid of the coefficient. So I can't add or subtract logarithms. I can't use the product or quotient rule until I've got those coefficients of the logs being 1. So make sure you apply that first. So a couple steps on that one. Now with that said, all right, make a note here before we move to our next one. Remember, we're always rewriting it exponentially when we're evaluating a logarithm. So once we've simplified it down. Now in our next example, we see a case of the product rule. So now you look at it, what are we doing? We're adding 2 logs together with the same basis. So adding or subtracting logarithms with the same base, we can combine those. So we're going to use the product rule this time. So I'm going to write the rule over here and then apply it. So log base, so instead of dividing m and n, what happens if we multiply m and n? So the property states that's equal to log base a of m plus log base a of n. So there's my m and n, so to speak. So using the product rule, this is log base e, right, or natural log. I'm not going to write log base e. Let's put natural log. This is the natural log of e to the 7th power times 1 over e cubed, right? So there's that single logarithm. So there's the product rule, right? Using the product rule allows me to combine a sum of logarithms. So we just added two logs together by taking the product of what we're taking log of. Now we need to simplify that. What is natural log of e to the 7th times 1 over e cubed? Well, we can go ahead and combine those. E to the 7th power, right, over e cubed, right? That's e to the 7 minus 3 power. Using exponents, we can combine by subtracting. That's e to the 4th, right? Natural log of e to the 4th power. And now we got our same base rule, right? This is log base e of e to the 4th power, which is equal to 4. So we can simplify that down, right? So that's using your properties, right, of logarithms, product rule, quotient rule. How about examples A and B? Let's go ahead and look at using the product power quotient rule in these next two examples. Log base 4 of 64 times x to the 5th power. So it wants us to expand this logarithm, break it up into a sum or difference. It says you should not have any radicals or exponents in your final expression. Well, first thing I'm going to do in this example is I'm going to apply the product rule that we just mentioned. We just went over. So product rule, right, says we can take these factors. We've got a 64 and a x to the 5th power. So that's going to be equal to log base 4 of 64 plus log base 4 of x to the 5th power, right, using the product rule. And with that, well, let's go ahead and simplify. What is log base 4 of 64? We can go ahead and evaluate that one. So over here on the side, if you need to, we can write it out here. What power, right, what exponent do you raise 4 to get 64? Well, 4 cubed is 64. So if you wanted to prove it with exponent properties, 4 to the y power equal 4 to the 3rd power, which means that y equal 3. So yeah, our logarithm, base 4 of 64, is equal to 3. All right, so we'll go ahead and put that in there. And then plus log base 4 of x to the 5th power. Well, we don't want any exponents. So in our next step, right, we're going to apply the power rule. So using the power rule, this is 5 times log base 4 of x, right? So there's an application of our power rule. Power becomes the coefficient. So now we have no exponents, which it didn't want, right? It said we shouldn't have any radicals or exponents in our final expression. So we expanded that single logarithm, right, using the product rule because we had some factors, right? We had log base a of m times n, right? Log of m plus log of n. All right, let's do the same thing with example B. Let's see if we can break this one up. Now you see here we got a quotient, right? We got m divided by n. So let's go ahead and apply the quotient rule. So using the quotient rule, log of m over n is equal to the log of m. This is a log base 10 logarithm. So log of x cube root of x to the 4th power minus log of the denominator, which is yx squared. All right? So there's the quotient rule forming a difference. All right, now, well, I want you to notice we can expand this and we can get rid of this radical. Remember, no radicals. Let's go ahead and get rid of that cube root. So log of cube root of x to the 4th power That's x to the fourth raised to the 1/3 power, right? Radicals are rational power. Square root's 1/2, cube root's 1/3, fourth root's 1/4. So we'll go ahead and convert that over to an exponent, and that way I can use, right, the power rule, right, in my next step. Now in our next logarithm, I'm going to go ahead and use the product rule. So log of m times n is equal to the log of y, right, plus the log of x squared. Log of m, right, plus the log of n. There's the product rule being used, breaking it up into a sum of logarithms. And now let's go ahead and apply the power rule, right, because we don't want to leave exponents. So again, these powers here, we're going to bring those down. So this 1/3, right, it's going to become the coefficient, just like this 2. So as we look at that, we've got 1/3 times log base 10 of x to the 4th power minus log base 10 of y plus 2 times log base 10 of x. So again, we've expanded that logarithm, right? We broke it up. Now, one thing I want to notice, we still have an exponent. So let's backtrack real quick here. This 4 here is still in the power. We should have gone ahead and combined these. So I'm going to go ahead and do that. All right, let's go ahead and clear out this last one. All right, let's look back at this last one here. So we had what? Log of x to the 4th power raised to the 1/3 power. Well, what is 4 to the 1/3 power? That's x to the 4/3 power. So again, using the power rule, right? Now let's go ahead and bring that down. So I need to take care of that exponent. So we should have combined those first. So we'll go ahead and do that. Well, it's equal to 4/3, right? Log base 10 of x. All right, so again, make sure there's no powers, no radicals, right? It says you should not have any radicals or exponents in your final expression. So now we've taken care of that. So remember, power to a power, you multiply those exponents. So using my property of exponents, right, a to the x power raised to the y power is equal to a to the x times y power. So again, applying that right here. All right, so I hope that helps you with your properties of logarithms. All right, and we'll use those in a little bit when we start to solve equations. So we'll talk about the product, all right, and the quotient rule as we start to solve some equations of logarithms, because we're going to have to combine log x terms. We're going to have to add them and subtract them, get them together to solve for x. So we'll stop there and continue in a little bit.